All right, so sections 11.2 and 11.3 are on similar triangles. Yesterday we talked about similar figures. Today we're talking about similar triangles specifically. So this slide shows us that one set of congruent corresponding angles is not enough to determine that two triangles are similar. We can see the triangle ABC on the left. Angle A measures 48 degrees. Triangle DEF on the right, angle D measures 48 degrees. Angle A, angle D, they correspond to one another. But the other two angles are not congruent, and you can clearly see that these triangles are not similar, right? So we take a look at what we call the similarity shortcut. These are almost like the triangle congruence shortcuts, except we're dealing with similarity instead of congruence. So if two angles of one triangle are congruent to two angles of another triangle, then the triangles will be similar. So just to summarize here, the angle-angle similarity shortcut makes sense because of the third angle theorem that we learned earlier in the year, that if two angles in one triangle are congruent to two angles in another triangle, then the third angle in each triangle, they have to be congruent to one another. And then, building off of the definition of similar figures or similar polygons from yesterday, we know that when they are similar, corresponding angles are congruent, right? So the angle-angle similarity shortcut is exactly that, a shortcut to both of those things. All right. So let's take a look at the sides. So it says two sets of proportional corresponding sides are not enough to determine two triangles are similar. So we have the examples here. We have triangle WBG and triangle JFK. And we can see the ratios up here. 54/108, so that's side BG, which corresponds to side KJ. That equals 1/2. Then we have 48/96, that's side WG over what would be FJ, and that also equals 1/2. So we see those two sets of corresponding sides are proportional. They both equal 1/2. However, that doesn't mean that WB and FK would also equal 1/2. And we can clearly see from the picture here that these triangles are not going to be similar, because angle W looks like it might be a right angle, and angle F looks definitely not like a right angle. So the question is, how many sets of proportional sides do we need? 3, right? Side, side, side similarity shortcut. If the 3 sides of one triangle are proportional to the 3 sides of another triangle, then the two triangles are similar. So next we have a side angle side similarity shortcut. And it simply states that if two sides of one triangle are proportional to two sides of another triangle, and the corresponding included angles are congruent, then the triangles are similar. So the one question remains, is side-side angle a shortcut for similarity? We know it's not a shortcut for congruence. Recall from chapter 4 that side-side angle did not work for congruence because you could create two different triangles. Those two different triangles were neither congruent nor similar. So no, side-side angle is not a shortcut for similarity. So what we're seeing here in the triangles, we start with triangle STU, this triangle right here, and we have triangle PQR. So side-side angle adheres to these two triangles, and those two actually are similar. But because it's side-side angle, we don't have to end up with PQR. We could end up with PQR over here, right? Because nothing says that angle Q has to be congruent to this angle T. And as long as QR is proportional to TU, which over here, see it's 2y, and here it's 2y, that angle Q could be a very different angle, resulting in a very different triangle that is not similar to the original triangle STU. So side-side angle, not a congruent shortcut and not a similarity shortcut. All right, so this is what is called a career connection in your textbook, and this is right out of the book. It says similarity plays an important part in the design of cars, trucks, and airplanes, which is done with small-scale drawings and models. This model airplane is about to be tested in a wind tunnel. So think about building an airplane. It costs a lot of money, a lot of resources, a lot of materials, a lot of people to build an airplane. Well, no airplane company is just going to, from scratch, go from what's on paper to trying to build an actual airplane, right? They're going to test models like aerodynamics of an airplane, aerodynamics of a car, things like that. And here's a picture, pretty cool picture. We have the wind tunnel in the background, and we have this model of this airplane. And they're going to stick that airplane in there, and they're going to study the aerodynamics of that airplane. And eventually, after they do all the research and they look over things, they'll come to a conclusion, hey, do we need to tweak things? Or, hey, are we ready to put this thing into production and actually spend the money to build it, right? So similarity can be very applicable in the real world. All right, last thing. So this is an example of applying similar triangles to a math problem. It says a person 5 feet 3 inches tall casts a 6-foot shadow. At the same time of day, a lamppost casts an 18-foot shadow. What is the height of the lamppost? All right, so to solve this, we're going to set up a proportion, right? And this is a pretty simple example. Lots of different proportions we could set up, and they would be correct. We talked about that yesterday. I'm going to take the height of the man, 5.25, over the shadow that the man created, and set that equal to the height of the lamppost over the shadow that the lamppost created. So there's my proportion, and now I need to solve for x. Cross multiply to solve a proportion. Well, in this case, I don't actually have to do the entire cross multiplication. I just need to solve for the x. So I'm going to multiply the 18 times the 5.25 and then just divide it by 6. Right? And that'll get me my x to come out to 15.75 feet. Simple example. When you get examples, not examples, but problems like this, they can be more difficult in terms of the setup. This one's pretty straightforward. They're both right triangles right next to each other. Read a problem carefully, and if there's no diagram, draw and label your diagram carefully. Then apply the proportion.